let's do another example of calculating the arc length of a curve parametrically. And TLDR from the last video is this formula will give you the length of a curve if it's a parametric equation. And, you know, we had a similar equation for rectangular functions or explicit functions. And we'll look at another one for polar in just a minute in the next and hopefully last video for you guys to worry about here before spring break. Okay, but yeah, you know, essentially, let's say we wanted to know as we travel along this parametric equation, how long is it? And as we all know, the circumference, this is describing the circumference of a circle. The distance around a circle, or the length of it, is 2 pi r, in contrast to the area, which is pi r squared, which, you know, doing the area was much easier to do using polar coordinates. And this is also true of the circumference of a circle. Anyways, let's just go with the example just to practice one more time. So again, our arc length should be equal to the integral of, well, what we want to know is, well, what's dx dt, what is dy dt, so that we can square them and plug them into our formula. So the derivative of x with respect to t is negative r sine t, and derivative of y with respect to t is r cosine t. So we need to integrate across the parameter t, and so we want to integrate from 0 to 2 pi because that constitutes a full circle with respect to our parametric coordinates, and we take the square root of those things squared, and so of course that would give us r squared sine squared t plus r squared cosine squared t with respect to t. And, you know, interestingly, the derivative of parametric equation of a circle is actually also still a circle, well, just with a negative radius, which is a little bit anyways. So we square those things, and just, you know, these structures we've seen many times before, but what we end up with is r squared, common factor, and what remains if we factor out r squared is sine squared plus cosine squared. Sine squared plus cosine squared is equal to 1 by fundamental Pythagorean identity, and so we're just left with the integral of from 0 to 2 pi of the square root of r squared. Because, again, sine squared plus cosine squared is equal to 1. Square root of r squared is just r, which could even be factored through our integral. So integral of r from 0 to t with respect to t. And the integral of 1 is just t. So we end up with r times t evaluated from 2 pi to 0. And if we plug in 2 pi, we'd get 2 pi r minus 0, of course, which gives us 2 pi r, or the circumference of a circle. And again, nice and neat, works out. Again, more further confirmation of that this arc length formula is doing what we expect it to. And of course, we could use it for any parametric curve, you know, where often that integral will be quite horrible.